In this example, we're going to be working with an aluminum nucleus, which will be flying horizontally just above a long straight wire. And the idea is that this thing was flying, and then this wire was turned on so that 4 amps of current was going through the wire. So here we go. At this point, try to draw your own picture and see if it matches mine. So we need the magnetic force experienced by the aluminum nucleus as soon as the current is turned on. That means we should first try to determine the direction of the force. So using this first right-hand rule, we can show the direction of the magnetic force. And now something to keep in mind, this aluminum nucleus, if there was no current in this wire, would just continue on its straight path forever. But as soon as we turn the current on, that current establishes this magnetic field, and that magnetic field will affect the moving charged particle. Because it's an aluminum nucleus, we know that it's a positive charge, and so if we point our fingers in the direction of the velocity, and we curl them in the direction of the B field, while the B field around the aluminum nucleus is into the page. So in order to do that, I have to flip my hand, and I can then curl my fingers down into the page, and I will get a downward force on the aluminum nucleus. So again, we point our fingers in the direction of the velocity, curl into the direction of the B field, and we get a magnetic force on our particle that would be downward. And so what we used the right-hand rule number 1 on was FB equals QV cross B. And so using right-hand rule number 1, we showed that this is a downward force on the aluminum due to the external field produced by the current-carrying wire. And now we can just determine the magnitude of that force. Keep in mind that any cross product turns into QVB sine phi, where phi is the angle between V and B, but that's 90 degrees since V is to the left and B is into the page at that point. And so sine of 90 degrees is just 1. So we get FB equals QVB, and we can solve the problem. So we don't know B, or do we? Now is when we use the new material, so recall the B field for a long straight wire is equal to mu sub O I over 2 pi r. And so we really do know B. That means FB is that QVB, but this is B, so we could have written from the initial, or from the beginning, QV mu sub O I over 2 pi r. Now we can solve. FB is, and we have the 13 and we were given that we were 3 centimeters away from the wire, so it's 0.03 meter. So the final answer is that the magnetic force is equal to, and I'm going to put a negative sign here because it's pointed downward in the picture. And so we get 1.11 times 10 to the negative 15 newtons in the y direction. So that's one solution. We could have also written that the magnetic force is equal to 1.11 times 10 to the negative 15 newtons downward, if you want, as long as we indicate both magnitude and direction. There are other ways, but that's enough, and that's the final answer.